In Part 3 of Lecture 11, we will discuss scheduling disk operations. Most files are stored on magnetic disks, which offer most of the advantages of magnetic tape, as well as several others. Magnetic tape was one of the earliest storage media and is fairly inexpensive and reliable, but it's also pretty slow. Magnetic disks can be accessed much more quickly than tapes, and they can also be used for direct access much more easily, with a program reading data from anywhere on the disk without having to read a large number of other blocks of data in between. Disks consist of a series of concentric tracks on which data can be written, and these tracks are numbered from the outside going inward. Tracks are divided into smaller units called sectors, each of which can correspond to a block, the logical unit into which disk data is divided. Although smaller disks may have a constant number of sectors throughout the disk, this is not usually the case anymore. Usually, disks are divided into zones, each of which have a constant number of sectors. As you move toward the outer tracks, the circumference is larger and you can store more data. Therefore, there can be more sectors. There are two views of a disk's structure: the physical view and the logical view. The physical view involves the concentric tracks that are divided into sectors, as we saw before. The logical view involves an address space, which is linear. This is the view that the operating system usually takes of a disk drive. We could translate the track number and sector number into the disk address, but this is increasingly impractical. Most systems will reassign the disk addresses of defective sectors to spare sectors located elsewhere on the disk. In other cases, the variable number of sectors per track will make this difficult. While the one-to-one relationship does exist, it must be determined from the mapping. The same disk drive will contain a large number of files that different processes may have requested more or less at the same time. This means that over a certain time frame, the operating system will be attempting to complete several disk operations within a certain period of time. We have to remember that the operating system has to use its resources as efficiently as possible. This requires that when we schedule disk operations, that we try to minimize the time that it takes to perform each disk operation. There are three factors that determine how long a disk operation takes: the seek time, the rotational delay or latency, and the data transfer rate. The seek time is the time that it takes to move the read-write head into position over the proper track. The rotational delay is the time that it takes the sector being read or written to move under the read-write head. And the data transfer rate is how many bytes per second can be transferred from the computer to the disk, or vice versa. Of these three, the one that we can exercise the greatest degree of control over is the seek time. By scheduling the various operations in such a way that we minimize the amount of time that the read-write head spends moving, we can increase the amount of data that we can transfer in any given period of time. When a process asks the operating system to perform input or output from a file on disk, there are several pieces of information that it must also pass along. The most obvious is whether it is a read or write operation. The disk controller must know the direction of the data transfer. It must also know the locations in memory and on disk to which and from which the data is being transferred. Usually, the memory address will be from a memory buffer. It is important to remember that the commands that are passed to the disk controller are being done by relatively low-level procedures. As we discussed before, the disk address is indirectly related to the track and sector numbers. No matter how many bytes we are reading, the data transfer will be done in units of blocks. There are two main concerns when scheduling disk operations: minimizing the seek time, because it is the one delay in data transfer that we can control, and making sure that all the disk operations will be performed. Some algorithms make it easy to minimize seek time, but run the risk of starving some processes. Others will ensure that all disk operations will be performed, but do nothing to minimize seek time. To understand how these algorithms work, we will look at a set of disk operations taking place on a disk with 200 tracks in the order shown on the slide. The algorithm that is the most equitable is FCFS, first come, first served. Disk operations are performed in the order in which they are requested. The problem is that they can be scattered all over the disk, and the read-write head can spend more time traversing the disk than it spends reading or writing data. Let's assume that the read-write head is positioned over track 100 when we start handling the disk operations that are on our list of requests. We have to traverse 45 tracks to get to our first operation. While the next few are not so bad, we have two requests that require us to go more than 100 tracks to fulfill them. Had we reversed the order of these operations, we could cut the number of tracks traversed for these two operations from 258 to 184, a savings of 28%. SSTF, shortest seek time first, addresses the problem of going all over the disk by going for the nearest disk operations each and every time. As a result, you will always handle the disk operation on the nearest track. The only problem with this approach is that if you have a steady flow of disk requests in a limited area of the disk, you may never get to perform disk operations that are scheduled for other areas of the disk, leading to starvation for those processes. If you look at how we reordered disk operations, we can cut the average seek distance by half. But as I said before, if we had additional requests for reads and writes in the 30s and 40s, we might never get to those on the innermost tracks. Scan scheduling attempts to correct the shortcomings of both first come, first served and shortest seek time first by moving in one direction, handling the disk requests appearing on the tracks that it passes until it reaches the request on the highest track. Then it switches directions and handles whatever disk requests happen to fall out on the tracks that it passes. This is also called elevator scheduling because it handles requests in essentially the same way that elevators make stops. They go up, stopping on the floors they pass if the button is pushed until they reach the highest floor requested, and do the same thing as they go down. This is relatively fair. Every process's disk operation has an upper limit in waiting time, and it is also relatively efficient. It doesn't jump all over the place. You can see that it is almost as good as shortest seek time first, with an average seek distance that is only 0.5 tracks longer than shortest seek time first. The C in C-scan scheduling is for circular. Scheduling here works in only one direction, from the outer tracks inward. When it reaches the innermost track, it goes directly back to the outermost track without stopping anywhere to perform reads and writes. Then it scans inward all over again, stopping to perform reads and writes when and where requested. This is a little less efficient than scan scheduling because no work is done on the return trip. But it is a little more equitable because scan tends to favor the innermost and outermost tracks over the tracks in the middle. In our example, you will notice that there is no discernible difference in average seek length between scan and C-scan. The last 4 slides on scan and C-scan scheduling are not completely accurate. In scan and C-scan scheduling, the read-write head moves as far out or as far in as it can go before changing direction. But if there are no disk operations requested that involve those tracks, there is no reason to go that far in or out. Look and C-look scheduling involve going as far as there are disk operations requested. On a disk with 200 tracks, as you have seen in these examples, there would be no reason to go further than track 190 before reversing direction. No one uses random scheduling. It is used solely as a benchmark to which other scheduling algorithms are compared. It is considered the worst case. We want to see how much of an improvement other algorithms are compared to random scheduling. The random sequence that we obtained included 3 very long seek lengths, all of which are more than 100 tracks. This led to an average seek length of 67.7, which is considerably worse than even first come, first served. With so many different algorithms for scheduling disk operations, the best one may not be so obvious. Shortest seek time first is an obvious candidate because of the short average seek length. But on systems with heavier loads, scan and C-scan actually work better in terms of average waiting time. Shortest seek time first can lead to longer waits for requests that are further away on a busy disk drive. There are a few factors that help determine which algorithm will work best. The type of requests and their number influence performance. On a very lightly used disk drive, any algorithm, even random scheduling, can look good. But on busier drives, the tracks involved in disk operations play an increasingly important role in the performance. The location of directories and index blocks are another important factor because these are being read quite frequently and will generally determine where other read-write operations will occur. If the directory is on an outer track and the contents of a file in that directory are on an inner track, it's obvious that this will involve a longer seek length.